Well, I've just clocked in for the third of this year's Christmas lectures on time. Now, time is something that we never seem to have enough of. And part of the reason is because of these things. Computers, microprocessors and everything, mobile phones, all these types of gadgets, fast communications. But how fast can all this stuff get? Well, it turns out, to answer that question, we have to look into the bizarre, slightly strange world of quantum physics. Because it's because of the understanding of quantum physics that we've actually been able to develop all this stuff. It also turns out that it's through quantum physics that we've been able to develop the most accurate clocks that are currently available. Atomic clocks, giving us atomic time. And it's probably because of our understanding of quantum physics that we may eventually be able to pin down what time itself actually means. So how fast is this quantum world? A volunteer, please. Would you like to come down? Your name is? Sorry? Laura. Stand here, Laura. Stand there, please, Laura. Laura, I have here a gearbox. And Laura, I'd like you to turn this gearbox roughly once a second. Just turn the handle of the gearbox. Now, there's a pointer on the back of this gearbox. And as Laura turns it, roughly once a second, this pointer goes round once a minute. Okay, thanks very much, Laura. I'm going to stay there. I'm just going to connect a second gearbox, exactly the same as this first one, on the back. Now what's going to happen, Laura, would you keep turning this way? Now that Laura's turning it, this pointer's turning around once a minute, and this second pointer is actually going to be turning around once an hour. We're multiplying up time. Now what would happen if we carried on connecting gearboxes? Well, that's what we're going to do. We're actually going to bring on another 8 gearboxes, connect them to these two, and see what happens. Laura, would you come and stand here? I'm going to connect up the boxes. Now, Laura, carry on turning. Doing a great job. So as Laura turns this once a second, this first pointer turns round once a minute, and the second pointer turns round once an hour. Now, I have a question for all of you. Because all these gearboxes are connected, they're all multiplying up time in exactly the same way. How long has poor Laura got to turn the handle at that end such that the pointer at this end goes round once? So can I have some suggestions, please?
24 hours.
24 hours? Okay. Any advances? 24 hours? Any more?
32 hours.
32 hours? A month? 6 hours? Okay. Okay. Who said a year? You're the closest. But you're actually still a long way off. Because wait a minute, wait. The answer, I don't think you're going to get it. Because the answer turns out to be 19 billion years. And that is longer than the age of the universe. You could say that it's longer than the age of time itself. So I don't think we'll make poor Laura try and turn it round. Thank you very much, Laura. Now, if you don't believe me, no reason you should, we have here the times. Laura was starting off with 1 second, goes through a minute, an hour, and then it starts to scale up. 150 days, 25 years, and eventually you reach 19 billion years. Okay, now we're going to run this in reverse. Because what I want you to imagine is that this pointer at the end down here is now actually turning once every second. So we're going to make it turn once a second. So how quickly is this handle that Laura was turning here? How long is it going to take for this handle to actually go round? Well, actually, the time is 1/600 million billionth of a second. And this is the quantum world. These are the types of times and the timescales that we talk about in the quantum world. Pretty short, right? In fact, this is far shorter than anything we could possibly imagine. So how is it, first of all, that scientists early on in this century actually hit upon the quantum world? Why do we need the quantum world at all? And that's what we're going to start to investigate. In fact, the story of quantum physics started with an oven, a pizza oven, any oven, just any hot object emitting energy. This is for those kind of individual pizzas here. Got to put on the protective goggles and the gloves, because when I open this oven up, you're going to see the oven itself is glowing red hot. The light and the heat that's being emitted is actually just waves. They're all part of the electromagnetic spectrum. And it's really hot. We know that, and we can feel the heat. Some of you in the front might actually be able to have felt that heat coming off. But that's precisely what troubles scientists. If they added up the amount of energy coming off in the electromagnetic waves, and that could be heat or light, the whole range, the amount that they calculated was far greater than the amount that was actually coming out of the oven. In other words, the amount of energy calculated using the wave theory of light that was around at the beginning of the century and worked perfectly well for everything else didn't seem to fit the experiment. Now, to show you what's going on here, and to actually show you the experiment that led to the understanding of the energy carried by light, we need to do an experiment involving electric charges. You've seen the machine, now I need the volunteer. Would you like to come up, please? And your name is?
Philip.
Philip. Now, Philip, this experiment involves you being a king for a day. So if you'd like to put on a crown, if you'd like to stand on that stool. Now what this does, this generates electric charges, and these electric charges are what we need to carry out our experiment on the energy of light waves. So first of all, to show you how it works, I pass this belt around, it generates charges, it passes the charges to the top of this generator. So Philip, would you like to put your hand on top of the generator? Okay? Right. So, what I'm going to do now is I'm going to generate charges on the top of the Van de Graaff generator, and these charges, because they're all the same charge, are going to try and get away from each other. So they're going to pass on to Philip, and they're going to go to his head. In fact, they're going to pass on to his crown, and the paper on the crown is actually going to rise up. That's great. Well, I think it looks rather good. So what's happened is the charges, because they're trying to get away from each other, they've actually passed on to these pieces of paper, and the paper's flown up in the air to try and separate the charges. Okay, since Philip's still isolated, the charges stay there. But if I ask Philip to step down, then it'll all discharge. Okay, that's great. Thanks very much, Philip. You'd like to go and sit down. So we know how to generate charges, and these charges we're going to now use to investigate the energy given off by light. So here we're going to bring on something that actually involves something like the Van de Graaff generator. In fact, over here we have the equivalent of the Van de Graaff generator, and this plate on top is Philip. Well, Philip's crown. Because what we have here is a gold leaf, 2 gold leaves that are actually together at the moment, and they're connected to a metal rod, and on top is this metal plate, and it's all part of the same thing. It's all isolated. So I can actually take some charges, and here they're just connected to we've just connected this crocodile clip to a circuit. So I can actually place some charges on here, and you can see that just like Philip's crown, the leaves fly apart. But I can discharge it to show how the charges can leave. But I'm interested not in discharging it with my finger, but I'm interested in trying to discharge this with light. In other words, I'm interested in how much energy I need to actually knock the charges off of this plate and therefore discharge these leaves. So these leaves are detecting the presence of charges. Now, if I come over here, where we have the lamp, here I have a control for the brightness, and at the moment we have it set up so that the colour of the light being produced by the lamp is actually red. You can see that the leaves are still separated, so there's charge still on the leaves. Now if I increase the brightness of the light, just about to see it being increased, the leaves are still separated, so the charge remains on these leaves. But now I'm going to take it down to its dimmest level, and instead of changing the brightness of the light, I'm actually going to change the colour. What I'm going to do to change the colour is actually go up in frequency. By going up in frequency, I pass from red through to green. You can just about see the green appearing now. And then I pass through to blue. There's the blue. Leaves still separated. So there's still charge on this thing. Now I pass out of the visible spectrum, and we're going into the ultraviolet. And now you can just about see that we're in the ultraviolet, and these leaves are just about beginning to come together. So the colour made the charges leave. The colour determined whether the charges leave, not the brightness. This was the start of the quantum revolution, because this interpretation, or this experiment to interpret it, if you try to use what scientists knew at the time about energy in waves, it doesn't work. I guess the waves that we're most familiar with, ones at the beach. Imagine we're at the beach. We're going to think about how much energy it would need to move some of the pebbles at the edge of the beach. When it's a calm day, when the waves aren't very big, we wouldn't expect many of these pebbles to actually be moved. But if it was a really kind of rough day, you expect when waves are big, they've got lots of energy in them, they'll do things, they'll kick the pebbles. The light waves will kick the charges out of that plate. But that's not what we saw. It didn't matter how bright the light was, it was the colour that determined whether the charges left. it's basically the same problem as with the oven. Somehow the calculation for the energy in a light wave is not giving the right answer. It's not predicting the right things. It's not agreeing with what's observed experimentally. It's actually Einstein at the beginning of this century who managed to make a breakthrough with this problem. He was particularly interested in the one that we saw with the electroscope. He couldn't understand it. What was wrong with this wave theory of light? So he thought about it and he thought, wait a minute, these charges have got to leave the plate. They must be kind of hit by something. Got to be hit by something in order to leave. We're thinking of light as a wave. Can't we think of it as a particle? In fact, that's what he said. That light should be thought of as a stream of particles. If I take these two snooker balls. Here's a particle. It's red. What Einstein was saying was that a red particle of light has less energy than a blue particle of light. So what he was saying was that the energy of this particle depended on its color, depended on its frequency. There was a packet of energy, and he called it the photon, and it was a quantum of energy. And that was the birth of quantum physics. We're going to test that out. We're going to see if Einstein can actually explain the experiment we saw, if Einstein's theory works. And I need a volunteer for this. A volunteer who's recently been to a fairground. No, can be anyone. Would you like to come up? What's your name?
Daniel.
Daniel. Any good at coconut shies?
Sometimes.
Okay, let's see if today is one of those times. So Daniel, what I want to do is, first of all, I'm going to pass you these red balls. See if you can knock off one of those coconuts. Aim more than strength. Ah, right, okay. All right, okay, well, you've had 2 hits and nothing's yet come off. Nothing wrong with your aim there. Maybe it's something wrong with the balls.
They're soft.
They're soft and they're light. Blue balls? Let's try blue balls. Now, these are heavier. Let's see what happens. Oh! You've done this before.
Yes.
Wonderful. You did it. That's it. Thank you very much.
Yeah.
What we just saw was exactly what Einstein was saying. That it doesn't matter how many of these red balls you throw, you're not going to dislodge one of these coconuts, which is one of the electrons on the plate. Throw a blue ball, and you can do it. The actual energy in the photons is determined by their frequency, by their color. And that's why in the experiment that we just saw, it was the color that was determining when the charges would actually leave the plate. So Einstein was right. In fact, it set off the whole quantum revolution, because it turns out that this kind of double secret life of light, the light and the light being a wave, the light being a particle, was actually true for electrons. Now, electrons are charges, such as the charges we generated in the Van de Graaff generator. And electrons live inside atoms. But it was J.J. Thomson that discovered the electron. He was interested in these negative charges, and he found that he could explain what was going on by saying that there was something called an electron that had a negative charge, and it was a particle. But things got a bit complicated in the Thomson household. Because 30 years later, after his father had been awarded the Nobel Prize for the discovery that electron was a particle, his son George got the Nobel Prize for saying electron was a wave. Now you can imagine what Sunday lunches in the Thomson household must have been like. Slightly complicated. Who was right, father or son? Electron's a particle, electron's a wave. Well, they were both right. Depends on the type of experiment you're doing at the time. That's what determines whether the electron behaves like a wave or a particle. A crueler way of saying it is that neither are right, because actually the electron is kind of somehow in between the two. Sometimes it just behaves like a wave, sometimes it just behaves like a particle. It's not just photons, quanta of light, it's not just electrons, it's also atoms. Atoms can behave like waves or particles. Well, we've got atoms in us. In fact, that's all we're made of. So in some sense, we also can behave like waves. It's just that we never see that effect in our everyday lives. Now, these ideas of waves and particles and things you like to think of as particles also behaving like waves, and particularly the electron, change then the vision of what an atom actually is. Now, old J.J. Thomson, he knew that in an atom there are an equal number of positive charges and negative charges, electrons. He just didn't know where they were. So, it being around Christmas, he came up with a Christmas pudding model. In fact, his model of the atom was precisely negative charges and positive charges. Negative charges like the current, positive charges like the nuts. Actually turned out not quite right. It was his student, Ernest Rutherford, who actually discovered that the positive charges weren't all spread out like the Christmas pudding model. They're actually concentrated in the centre. And so he thought, quite understandably, well, if I've got positive charges in the centre and these negative charges are doing something around, then it must be something like the solar system, right? Like the sun at the centre and then all the planets go around. That's what he came up with, so-called planetary model. Central, positive charge, negative charges going around. But wait a minute, George Thomson had discovered waves, electrons being waves. The electrons can behave like waves. So where does that put the model of the atom? Well, it took Niels Bohr, Danish physicist, who actually came over to study with Rutherford and with Thomson at the beginning of the century. Actually, he arrived in England from Denmark. Couldn't speak any English. He brought the entire works of Charles Dickens with him to learn English. But he seemed to do quite well, because he read them, worked out how to speak English, and then later proposed a model for the atom that actually, in a slightly modified form, actually survives with us today. That model is over here, and we presently understand the model of the atom, thanks to Bohr, in the following way. The positive charges, yes, are at the centre. But the negative charges, the electrons, actually are like waves around it. But how can we understand what this model is telling us? How can we understand what energies the electrons have? So for this, I need 2 volunteers. You two. Could you come up here, please? Now, your name is?
Carly.
Sorry?
Carly.
Carly. Stand there. Name is? Daniel. You stand over here. Now, what I'd like you to do, Daniel, is just turn this skipping rope. Just gently. That's it. Set it up. Steady enough such that it's actually going round. Right. Okay. Keep going. Keep going. Don't stop. So what Daniel and Carly have actually set up is, well, a fairly simple wave. And it's quite smooth. It's only got one curve in it. So Daniel, it looks too easy. Try and set up the second wave. So that's it. Bit faster, bit faster. Yes, well done. Now see what Daniel had to do. He actually had to increase the frequency of his hand. Actually, he had to put more energy into this rope. And the net result is, of course, we've got a wave that's actually got 2 curves in it. So this wave has more energy. Daniel, think you can go for 3?
I'll go for it.
Go for it. Okay, come on, Daniel. Keep going. Yes, 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 you got 3. Yes, well done. What about 4? No, don't.
You didn't go up to that much.
Oh, okay, right, don't worry. That's great. Okay, thanks very much. I'd like to take a seat. Thank you. So we just saw that the waves that can live on this skipping rope, very much like the waves that can live in this atom, had to have definite frequencies. There was a definite rate at which Daniel actually had to turn that skipping rope to get the waves set up. So it's a definite frequency, definite energy. That's key to understanding the energy of electrons in the atom. And that's eventually going to link in with our measurement of time. But first, I just want to show you what happens when electrons get fed up in one orbital, fed up at one frequency, fed up at one energy, and they want to change. Well, they can do. It's very much like us in a house. We could spend a lot of time on the ground floor, or we can go up to the first floor. Well, if you want to go up to the first floor, you've got to run up the stairs, have a chocolate bar, gives you a bit of energy, up the stairs you go. You can also come down. But you spend most of the time on one of the 2 floors. But when you come down from the first floor to the ground floor, you actually give out some energy, going from a high energy to low energy. What happens, since these are now definite energies, like the definite energies in the skipping rope, well, it's almost the reverse of that experiment we saw with the light in the electroscope. The electron is now going to give out energy, and it gives it out as a quantum of energy, as light. But since it's a definite energy and a definite frequency, it's a definite color. So a photon of light is emitted when an electron passes from the high level down to the low level. Now, in everyday life, we don't necessarily always see the electrons at higher levels. They tend to want to live at low levels. They haven't got enough energy. But everything, I said, everything in us is made of atoms. Everything in the world around is made of atoms. So all atoms can do these types of transitions. In fact, atoms in, well, this desk, in me, oh, in pickles. Let's have a look at the quantum physics of the pickle. As I said, we have to supply energy to get the electrons up to the higher levels. But once they're up there, they can jump back down, liberate the energy, goes off as a packet of energy, goes off as a photon. We should see some kind of light come off. Electricity, please. Elio? Whoa. Oh, it's like a street lamp. In fact, it's exactly the same principle as a street lamp. Thank you, Ilya. So the pickle, this dull old green thing, actually glows orangey. It's an orangey colour. That's because the electrons have made the transitions. Okay, well, I hope none of you have actually tried that, and you shouldn't try that. But maybe you've seen the effect in something a little bit more familiar. And for this, I actually have to slip on something a bit more comfortable. Gloves and my shades. Can't go anywhere without these. Oh, that felt good. That was a quantum effect. It was an ultraviolet light source. Very much like in the electroscope experiment. Lots of energy shone down onto the jacket. Molecules in the jacket Well, just emitted light. It got excited up to the higher level, emitted light in the visible. That's what makes your clothes look white when they come out of the washing machine, when you put the washing powder in. So this is quite useful, these kind of transitions between levels in an atom. For one atom, you can go from the first level down to the ground and emit light. Now you can imagine if you had a material where all these atoms were doing the same thing, they're all emitting but kind of haphazardly, well, you get some kind of light out of it and it will be reasonably bright. But what happens if you could get them to do it all at the same time? If all the atoms could make a transition down from that first level down to the ground at the same time? Well, we're just going to demonstrate what might happen. Now, I don't go around looking for applause, but I'd just like you to just clap. Okay, that's great. But now I want you to think of me as the lead atom, and you're all going to follow in time. Do exactly what I do at the same time. And now let's see what that sounds like. Okay, great. What you could see is it's much louder when we all do it in unison. So we'd expect far brighter light if all the atoms could be made to make their transitions in unison. And that's exactly the principle behind a laser. Over here, he has the laser source. It produces a very fine beam, just passing down the tube. And we've got a balloon at the end. This is a laser detecting balloon. And we're going to see exactly what happens when we turn up the energy in the laser beam. So he just turned it up. Laser beam's traveling down onto the end of this balloon. You could just about see the laser beam. So the balloon is now absorbing the energy of the laser beam. Oh, whoa! Great, thank you very much, Elia. So there's a lot of energy in a laser beam. That was just light. When you shine a torch on a balloon, it doesn't explode. That was a laser beam, and it has a lot of energy in it. By making an atom, or making the electrons in the atom, make transitions between outer levels and inner levels, we get off a definite frequency of light. A definite frequency means a definite number of oscillations per second, an enormous number. And if we were to count those up, we could use that to define the second and to measure the passing of the second. And that's the principle behind the atomic clock. But it's also the principle behind all of this stuff. Because it's our understanding of quantum physics that has enabled us to develop the computers, communications equipment, mobile phones, all the gadgets that we use every day. So I started off asking you, how fast can all this stuff get? Well, to see how fast all this stuff can get, we need to understand just a little bit about how all this works. The computers, while it looks complicated, it's actually quite easy how it works. This is one of the first computers. It's obviously hand-operated. It's an abacus. If I want to add together, here we have ones, tens, hundreds, thousands. If I want to add together, for example, 6 and 4, 1, 2, 3, 4, 5, 6, and then I add another 4, 1, 2, 3, 4, that makes 10. That registers a 10. But of course, you've got to be fairly skillful to do this quickly. And it would be nice to have a mechanical device that did it. And it was actually this man, Charles Babbage, who gave us the designs that actually form the basis of our present-day computers. Now, Charles Babbage was actually motivated for this by a very real need. There were a lot of ships being lost at sea, and they were using these navigation tables that were around at the time with calculations made by hand. And a lot of the errors in there he thought could be avoided if it would only have a machine that could actually carry out these calculations and check the tables. So he came up with an invention for such a machine. In fact, he was interested in all machines that kind of add and subtract and keep track of data in a kind of ordered way. He even developed a clocking in clock for the factory, like the one I used at the beginning of the lecture. So his first machines were very much like clocks. They had cogs in them. They had spindles and cogs, and they worked in a very automatic, sequential type of way, very much like a clockwork of a clock. In fact, around the same time, a company that we now know as making computers, IBM, used to be called the International Time Recording Company, because there's such a similarity in the technology for building clocks and building computers. Of course, nowadays, we don't have any of that stuff, any of that mechanical stuff. It's all replaced by electronics. Computers like this use special kind of maths. So in order to understand how fast they can get, we ought to check out what that maths is. And over here, we've got part of the audience who volunteered to be a computer. So could you just hold up your numbers, please? Now what we've got here is at the back, we've got the numbers 1, 2, 4, 8, which are actually powers of 2, because that's how a computer works. It works with zeros and ones. It adds up to 2. So it works with zeros and ones, which are called bits, binary digits. So these are what we're going to see. These are the numbers of 1, 2, 4, and 8 that we're actually holding up. They're just the register at the back. These are the guys who are actually going to do the storing of the numbers. And at the moment, we see we have no 1s, no 2s, no 4s, and no 8s. So we're registering the number 0. So I think we'll add 1 to this computer. So just turn your number over. No, not you, no, that's it. It's a fast computer, but it's not that fast. Okay, so we're registering 1. Let's add another 1 to it. So that makes 2. So you turn yours over, you turn yours back. So now we're registering the number 2. Add 1 to it, makes 3. Turn yours over. Now we're on to 4. Now you turn yours round, and you two turn yours back to 0. We're up to 4. 5, 6, 7. You have to work the hardest. 8. 8 is now 1 on the end, and all of you back to 0. No, you keep yours as a 1, and all you 0. That's it. That's 8. Thank you very much, the computer. So that's what computers do. They actually process 1s and 0s. But how do they do it? Well, computers are physical things. They're physical machines. They need to be made of something. So we need to understand that. This is what they're made of. This is actually a block of silicon. So you don't need the whole block. All you need to do is just shave off a slice of it. And this is what I've got here, a silicon wafer. In fact, it's already had printed on it a number of circuits. I believe there are around 50 on here. So the silicon wafer is actually cut up, and a bit of it is placed in this, which is a microprocessor. It's a bit difficult to see what's going on. So we're going to bring on a microscope and hand it over to Ilya, who's going to have a look. So Ilya, if you could just line that up for us, please. Now what you can see, we just caught the edge of one of the leads on that silicon chip. So Ilya, if you move across and let's have a look at the transistors. And actually so small, of course, that you can hardly see them. This is really incredible, the way that they get all of this detail onto this silicon chip. Thanks very much, Ilya. Now there's a reason that it has to be so small. The reason is, quite simply, that if you want to make something very fast, you don't want to spend a lot of time shuffling the data across the chip. So that's why the drive for computers is to make them smaller. It's not just so that they fit in the pocket, so that they're faster. And here we can see a chip in action. And what we're actually seeing, every time the lights come on, we're actually seeing which bits of this chip are actually processing the data. It's almost like looking at a flow of traffic through a city. We're seeing which of the roads are actually carrying cars at any particular moment. But all that's just technology. What does physics say about the ultimate limits of data processing? How fast are our lives going to get using these high-tech devices? That's what we're going to start to look at now. First of all, we have to see not only how fast a computer is, how fast is a communications network in general. Well, here I've got set up a program that will actually just send a message somewhere in the world. It's actually sending it to Minneapolis, sending it to Minnesota in the United States. So if I press return on this, so what's happening is that this machine is actually sending out a message, actually 4 times, and timing the flight of the message to the United States and back. And here's the average down here, 116 milliseconds, 0.116 seconds. That's quite fast, go all the way to Minneapolis and back. But if we work out how long it would have taken light to travel that same distance, it actually works out to be 30 milliseconds, which is 0.03 seconds. So the message actually only traveled about a quarter the speed of light. So while it's fast, it's not quite fast enough. There's plenty of room for improvement. But why can't we send messages at the speed of light? Well, let's have a look at what happens when you try to send messages quickly. For this, I need your help. In fact, I need the help of 2 rows in the audience up here. Now, you 2 rows, what I'd like you to do is I'm going to show you 2 on the end a message. I want your neighbours to turn away. Just have a look, memorize it, pass it back. Right. I'm going to come down to the front. Now, you 2 rows are 2 communications links. And when I say go, I want you to whisper the message to your neighbour and pass it on. When it gets to the end, put your hand up. Okay? You 2 at the end. So ready? Are you ready? Put your hand up if you're ready. Great. Part of the network's ready. Okay? 1, 2, 3, go. Now it's a race, because we're all trying to decide which network to subscribe to. So come on, get that message down. Oh, I think this row won. Okay. Now, could you tell me what the message was?
A, B, C, D, E.
A, B, C, D, E.
A, B, C, D, E.
A, B, C, D, E. You're both wrong. Not by much. It's A, B, D, C, E. So you can see what happens when you try to send messages quickly. Errors creep in. That's why taxis and other people who use mobile communications often say things like Alpha Foxtrot Romeo. They make the message longer. They're trying to say AFR. They make the message longer to try and correct any errors, to at least reduce the possibility of introducing errors. So we can see that there's some kind of limit on the actual transmission of the data. But when we send a message from London to Minneapolis, we're not only passing through optic fibers and through satellite links, we're passing through some machinery, some computers that are actually going to route this data. So how can we make the machines faster? Well, the machines are made of silicon, or at least the active bits of them are. And silicon is nothing other than sand. So scientists are currently looking at other materials that might actually have faster transitions for their electrons between levels, that might actually make faster transistors for computers. And here are some of the things they've come up with. It's a lump of coal. It's actually the carbon in this. Has some very interesting and possibly useful electronic properties. The cling film, actually this is made up of polymers. And these are very long molecules. These can act like wires in a circuit. And here's a bit of spinach. Now, personally, I don't like spinach, but I wouldn't mind it in a computer if it made the computer faster. And it turns out that the molecules that make spinach actually have some very fast electronic processes in them. And that could be very useful for future computer technology. So that's one thing you could do. You look for new materials. There's another thing you could do. You can try and get these electrons to behave properly. Now, each of these chips contains lots of electrons doing lots of things. If you could get the electrons to all behave together as a crowd, to group together, not only might that be good for storing data, you actually might be able to pass on data throughout the computer quickly without introducing the kind of errors we saw up there. And this is where scientists are turning to quantum physics to look for possible ideas. And I'm going to show you an effect of quantum physics, which is currently being investigated to actually include in computers. Now, what Elia's bringing on is a tray containing something called a high-temperature superconductor. That's that grey blob in the middle. But the high-temperature superconductor only behaves as a superconductor at very low temperatures. That's why he's poured in liquid nitrogen into this. Because what happens is as follows. As you lower the temperature of this superconductor, the electrons in the material get a chance to actually act as a crowd. Usually they're kind of being buffeted around by the other atoms in the material. But when you lower things down in temperature, they can act as a crowd. In fact, what they do, and hence the word superconductor, is that this crowd is so strong that it can kind of march through the material without any resistance. In fact, that's the key. It's no resistance. It's a superconductor. And we're going to see what the effect of that is. Because if there are electrons marching around as a group, that's actually like a current. And the current gives rise to a magnetic field. So I'm going to put on these goggles, and we're actually going to check out what magnetic field and whether there's a magnetic field coming out of this material, and therefore if it's acting as a superconductor. And what I'm taking here is a tiny magnet that I'm actually going to place on top of the superconductor. Ooh, although I tried to place it on top and it's actually floating. Now this is bizarre, but that's what you get in the quantum world. So that's where things are at. That's what scientists are trying to do, to speed up electronics communications. But what does nature say would be the ultimate limit? Now, if we think back to our atom here, and we think about our computer, remembering that the computer actually acts basically like a clock. A lot of these chips here are adding up numbers, but a lot of them are actually acting as a clock to regulate the traffic on the chip. Now, how fast could that clock get? Well, this thing runs at about 300 megahertz. That's 300 million cycles per second, 300 million oscillations per second, 300 million times per second that this chip sends out an instruction to the rest of the machine. But if we look at the atom and we ask, well, what's the frequency associated with a transition between this outer level and the inner level? Or what's the frequency associated going from the first floor to the ground floor? We actually get 1,000,000 times this. It's 1,000,000 times 300 megahertz. 1,000,000 times faster. So that's bad news for future Christmases, because there'll always be a faster machine. But clocking the information is only part of the problem. If we're trying to build a super-duper computer, we actually need to store the data somewhere. And smaller means faster. So let's think about the limits of storage given by nature. Let's have a look at this atom. We have two orbitals. The electron could be in the inner one or the outer one. The electron is on the ground floor or the first floor. 0, 1. This is very much like the binary digit needed for a computation. So, how small a piece of material would you actually need to store all the information from all the printed books in the world? That's what we're going to look at. And I need a volunteer. Your name is?
Zen.
Zen. Would you take this 1 and go to the top of the stairs and just stand there? Turn round and hold up your 1. And I also need this row to help me with the calculation. So we're going to start off by thinking, how many countries are there in the world? We're only going to do it roughly. So we're going to guess, what, 100? So we just put 100 up there. So would you two stand up with your zeros? That's it, 100 countries in the world. How many major libraries do each of these countries have? Should we say 10? Yeah, 10. Would you stand up with a 0? How many floors on each one of these major libraries? Should we say it's a 10-floor building? Okay. Would you stand up with a 10? How many shelves on each of the floors? Well, let's overestimate. Let's say 1,000. Would you stand up, the three of you, with the zeros? How many books per shelf? Infinity. Let's say 100. Would you two stand up? Now, how many pages per book? Well, let's overestimate again, 1,000. Would you three stand up with the zeros? How many lines per page? Should we say 100? Could you two stand up? How many words per line? Should we say 10? You stand up with a 0? How many characters per word? 10? Stand up with a 0. Now, any one of these characters could be any one of the characters on a keyboard. There are 26 letters, but also numbers and punctuation. So let's say 100 possible characters. So you two stand up with the zeros. And there we have it. So 1 followed by 18 zeros. 10 to the 18 bits of information in all the printed books in the whole world. Now, if each atom could store 1 bit, a 0 or a 1, how much, what size of device would we need to store this information? So you can sit down now. Thank you. What we're going to do is we're going to bring on the ultimate atomic storage device. We're going to bring on the device within which, if we were using atoms as storage, we could actually store all that information, those 10 to the 18 bits. So Ilya, would you bring on the ultimate atomic storage device? It's coming on. A little bit heavy. Thank you. So let me open it up. it's empty. In fact, it's not quite empty. Because somewhere down here, just about got it, there is a grain of sand. Because that's all you need to store all that information. One grain of sand. But oh, if life were that easy. We store ones and zeros on atoms. But the quantum world hasn't finished with us yet. Quantum physics has a sting in its tail. It goes back to the beginning of the lecture. At the beginning of the lecture, we said particles were also waves. So if you're trying to build a computer, you're trying to keep your electrons on one atom or another, you can't quite do that because they're waves. You never quite know where they are. In fact, the idea of this uncertainty is very similar to what would happen if you took a photo, first with very high-speed shutter. There I am. There I am. But what speed am I going at? Okay, let's slow down that shutter speed. Well, I'm obviously moving to the right because that blurring is giving an indication now of my speed. But where am I? Now that is the root of the uncertainty at the basis of quantum physics. And so, if we're trying to shrink down computers and trying to use atomic systems to build clocks, eventually we hit that uncertainty. So we should think probably not in terms of a computer, but a quantum computer. And not in terms of a clock, but a quantum clock. Now that's all for the future. And we'll be discussing a bit more about that in the last lecture. But in the next lecture, we'll be looking at how certain we can ever be about the future. Thank you. If you'd like a copy of the booklet that accompanies this year's lectures, please send a cheque or postal order for £4.95, made payable to BBC Education, to Arrows of Time, PO Box 7, London, W12 8UD. Credit card orders by telephone on 0990 100 789.